Okay, so what we're going to do today is we're going to look at how to do a practical deconstruction. Deconstruction. Anyone got any ideas what that means? Deconstruction. No idea. Okay, that's what I thought. So, Patch.
Break down.
Yeah, break it down. So it's all the steps involved in performing a practical. That's why it's called a deconstruction. You can say design, part of that's doing a procedure. So what you're going to need to have in front of you is your practical sheet, because our first deconstruction, and you've got to actually fill in some of the blanks, all right, and I will do it on the board behind me, but you're going to be doing it eventually on your A3 sheet of paper. Okay, and that's yours. We're going to practice today, and then shortly you'll be doing it by yourself, all right, again. But you can use whatever we've got here as a bit of the guide. But you have to do it under like test conditions a little bit later. All right? Okay, so our practical it's called acid content in question mark. So when we start to do our practical, whatever we are actually trying to work towards goes in the middle of our page, and we sort of, it's a bit like a concept map or a schematic diagram. You can call it a, what's the other thing for them? Not a star chart, it's got another name, okay? Knowledge wheel, okay? So we start to look at all the details about how we would do it. Now, you do this by yourself, and then a little bit later on you connect with a partner, and you'll have two of these. You'll have your design, and you'll have, okay, your partner's design, and then you'll say, oh, I like that about yours, or you'll just say, oh, yours is hopeless, we'll just do mine, okay, for whatever reason. So that's where we're heading with the actual design of the practical. So you do the initial deconstruction yourself, then you do the practical with the partner. Let me have a look at what you decide to do, and you probably haven't thought about this one yet. So depending on what you're talking about, and I said acid, let's assume and say we're doing the acid content in lemonade. Okay? That could be one of your practicals that you might be wanting to do. So all of these, if you haven't worked out already, if it's acid content in, probably the best method, but not the only method, is going to be based on a titration. And we've done an acid content in vinegar as a formative. So you know how we did that. So the whole idea was to use that as a scaffold to do your acid content in lemonade. Okay? So, but you've got to work out how you're going to do it. Now, increasing complexity. I've got a frozen lemon here because it just happens to be frozen. But let's assume you did acid content in lemon. All right? So you have to think about, well, how am I going to do that? So the first challenge for something like this is, how do I get the lemon juice out? How do I extract the lemon juice from the lemon? It's fairly obvious, okay, for most of you, I hope. But how do I do that? That's got a bit of a complex idea to it. Had students in the past do the acid content in things like pineapples, not so easy. Acid content in cabbage, not too bad either, all right? But if you're going to use something like that, it's a little bit more complicated, a few more steps involved, but how do I get the acid out of that? This is straightforward because it's a liquid already. I mean, it's fairly obvious it's got some acid in there, so you don't have to extract the acid, it's in there in front of you. I had a group a few years ago do acid content in, sour juice. This one is sour gecko. Right? Sour implies it's got an acid in it. And so if you're going to do something like this, all right, this is really complex. This is actually, according to the thing here, it's 19 grams. And I remember that when the students did this a few years ago, it took them a while to work out, well, I know this has got acid in it. How do I get the acid out of it? And we talked about methods to do that. And they worked out in the end that they had to sit it in water for 48 hours, okay, in order for it to leach out the acid. The acid, we assume, was water soluble. And then they had to do some tests on it to work out, well, did they sit it for 48 hours? Did they do it for a week? All this is unknown. You can't look this up on the internet the acid content in this or this. You've got to work it out yourself. So that was more challenging, all right? Just acid content in some sort of a sour lolly like that. All right, let's assume, for the purposes of today, that we're going to do acid content in lemon, okay? Pure lemon. And we're going to look at all the different variables that we would need to consider, some of the procedures we would need to consider, and some of the safety aspects as well, because all these things are going to surround our practical. All right, now, first thing you need to do when we look at any of this is you need to do a little bit of research on whatever the thing is that you want to get the lemon out of. The acid out of. So if I'm doing a lemon for my acid content in, I would need to ask some questions. First question is, what is the acid in lemons? I would need to know that, wouldn't I? Okay? I would need to know what is the acid in lemons. Okay? I might need to know about what variety of lemon is it, because, I don't know, this could be a Lisbon lemon. It might have a certain acid content compared to, say, another type of lemon. Because when you go to a garden centre, there's not just lemons, you've got about 12 different varieties of lemon to choose from. Or this could be a lime, it could be an orange, okay? It could be any citrus if you choose to do that. So that's some of the things we've got to do some research on. So what's the acid in there? What is the variety of lemon that I'm going to use? All pre-research stuff, questions you should be asking before, okay? Now, apart from that, all right, if we think about the research, we've got to think of a few other things, okay? So, in terms of our procedure, we sort of come up with a lot more questions as well. So the procedure would be things like, how to extract the juice from the lemon. I haven't given you all this, but these are things that you're going to fill in, okay? So how do I extract the juice from lemons? Fairly obvious, I'm probably going to have to use a lemon squeeze, all right? Other things you might need to consider. So I've got the pure lemon juice. And if I just grab my conical flask over here, so when we're doing the titration, okay, we have to work out, well, how much of the juice do I need to put in the lemon, like as in the flask? Do I use a mass, if you want to do a percentage weight by volume? Do I use a volume of lemon juice? How many lemons am I going to need? Because if I'm going to use, say, 20 mils of lemon juice, that's going to be a lot of lemons to squeeze, isn't it? So things you got to really think of down to the finest detail. So how to extract the juice? The other thing is how much of the juice that I need. So what volume do you think I'm going to need? I don't know, because we haven't done any practical yet. All right. Do I need to dilute? Do I need to dilute the juice by any factor? Do I need to dilute it, I don't know, by a factor of 10 maybe? Do I need to dilute it by a factor of 2? And then how do I do that? All right. But we talked about dilutions before. So this is just, we haven't even started it practically yet. So we're just trying to work out how do we get the juice out, do I need to dilute it, etc. Okay. What else do you think we need to consider? So we talked about how we get the juice out of the thing that we are experimenting with. What other things would we need to consider? Rocco?
Standard solution.
Good. What am I going to react it with? So, what am I going to use for my standard solution? Okay, now, hint, we use sodium hydroxide. Okay, we use sodium hydroxide because it was easy, but we do know that if we're going to use sodium hydroxide, that we would need to standardise the sodium hydroxide against a known HCl before you even start your practical. So if you choose sodium hydroxide, you would have to standardise it first. Alright? The next thing is also what concentration of sodium hydroxide do I need to make? Is it going to be 0.1 or 0.01? Alright? So you might start example with 0.1 molar, it's fairly standard, but then you might have to dilute it when you do some practice titrations with your diluted or undiluted lemon juice. I don't know. Okay? That's the beauty of this. I don't have the answers. Okay? Alright, so I've done my standard solution, I've got my juice, and obviously this is the procedure that will be evolving, and you have a bit of an outline, but you don't know exactly what you are doing until you actually have a go at it. Alright? And then you'll refine your procedure. We'll talk about why we do changes. Alright, what else do I need if I'm doing a titration? What else do I need if I'm doing a titration? Okay, how do we know when the base and the acid were equal according to stoichiometry? What do we use? Phenolphthalein, yeah. So we've got to have an indicator. Something to tell us that the endpoint is reached, okay? However, we could also use, some students last year used a pH meter, okay? And hooked it up to a data logger. Now, a pH meter tells us when the solution is neutral. Neutral means acid and the base have neutralised one another. In other words, the mole stoichiometry of the equation has been satisfied. So this is not so bad because this is colourless. If we're going to do lemonade, we can see the endpoint in that. If we're going to do this dissolving in water, that we can see the endpoint. And lemon juice is pretty okay. You can sort of see the endpoint. But if you're going to do something like, say, Coke, which is already like black, then you're going to have an issue about how do I see the endpoint for that titration. Students have done it in the past, but you've got to think, well, an indicator's not going to work. Okay, because Coke's black. Alright, so you've got to think a little bit more deeper about how you tackle that one. So these are questions that you will write in a very brief procedure, but things you've got to actually work out before you even do the experiment. This isn't an answer, this is a guide, by the way, about how to do it. Okay, so we've got research about what is in it, we've got procedure, what things do I need to work out in my actual design for the experiment. I also like to have underneath it, I like to see a diagram of what you are trying to do. It's not a perfect diagram, this is a plan. So what I like to see is, how you're going to extract your juice with a juicer or whatever. What are you going to have in your burette? What are you going to have, or what are we going to use in there? That's the other thing I've got excuse me, for procedure is, am I going to use a mass or I'm going to use a volume of the juice? And that doesn't really matter. If you're going to use that, probably going to do percentage weight by volume, but you could also do a volume and you could work out moles per litre milestone. You could work out the concentration. Because I haven't told you, I haven't put that in the practical, nowhere in the practical it says work it out in percentage weight by volume. Okay? I've got actually, well, I do, don't I? Is the content percentage weight by volume or weight by weight? I'm going to change that, alright? Moles per litre. You can work it out in concentration as well. So either one of those would be fine, but that means we did percentage weight by volume for the acetic acid as an example, so we actually weighed it out. Alright? If you're going to do it by volume, think about that one. If you're going to do it by volume, then you could do concordant titers. Because you're going to have a known volume in here. You're going to have a known volume in the flask. of whatever the juice is. And that's going to be consistent. 20 mils, 10 mils, whatever you're going to work out. Through trial and error, that's what it is. It's called science. In terms of what you're going to do. So we've got a bit of theory we need to work out. Are we going to do lemons, or we're going to do something that's a bit harder? We're going to do, Coke or whatever. So a bit of research first. Okay. Sort of going along with the procedure is safety. And so what I need to consider is things like what chemicals am I going to be using? Well, if you haven't worked it out yet, obviously you're going to be using HCl, maybe you're going to be using sodium hydroxide, that's the standard, and you know that those chemicals are caustic and corrosive. So therefore, then you would need to consider, alright, so I need to, obviously I'm going to have to wear some glasses, don't want to get contact on the skin, etc. Now the details of all the safety you do in your final write-up, but they're flags about the chemicals that you're going to be using. Okay, other things. Well, what equipment am I going to be using? Fairly obvious that you're going to be using lots of glass if you're going to be doing a titration, which I think we are. So we know the glass is fragile, sharp, so you've got to be careful about how you handle glass. Other things, well, some of you might look up a knife, alright, to cut things up with, maybe if you're doing a lemon, unless you juice it at home, of course. Some people have done that before they've actually juiced it all at home and just brought in the fresh juice. Oh, I just thought of something just then. The juice, okay? So if you are doing the lemon juice, you would need to consider, maybe over here, storage. And I'll put up here temperature. Because if you've just squeezed the lemon, and let's assume it's been sitting, in the open for 5 days, then it may deteriorate. The acid may get more concentrated. Okay? This has got water in it as well, so it might deteriorate. So one of the things you might need to be able to have to say for your procedure is you've got to use lemon juice within 24 hours of you creating the juice. Okay? If that makes any sense. Does that make sense? Everything's got a use-by date, okay, or a best before date, and there's no reason why that the juice of a lemon can last forever either. So that's something to consider when we talk about errors. All right, so we've got safety procedure. All right, variables. So we always, for all of our practicals, we have to consider some variables. We've got to look at the independent variable, the dependent variable, and what things are we going to keep constant. All right. Now, so what's the independent variable? What's changing in this, more or less? Let's make it easy. Dependent variable. What are we actually measuring? The acid content in this case, the acid content lemon. So this is going to be the acid content in the lemon, and that's going to come from where? How are we going to measure the acid content in lemon? That'll be the... So we've got the lemon in here, we've got our standard solution on the top there, so we're going to be recording... Is it the titer value that's going to determine that? We're measuring the titer value. That's what we're going to write down on our sheet of paper, isn't it? That's what we're recording, yes. So I think it's the titer value. Okay, what's the independent variable? What's changing? I think we're going to keep it simple because we're only doing one type of lemon. That'll be one of the constants, so we're not going to do 5 varieties of lemon. We could, because we're working backwards towards a hypothesis, all right? And so the independent variable is basically going to be the acid content, whatever that is, okay, in the vinegar. In say, I don't know, Lisbon lemon, if that's what we're going to use. I don't know what variety this lemon is, but it'll be the acid content in that. Okay, that's going to be changing, all right, over time, possibly. Now it's going to be variable. That's why it's the independent. Okay, constants. What things we need to hold the same?
Volumes.
Yeah. So when we're doing a titration, we've got to make sure that we have the same volume for titrations if we're doing concentration. What else has to be constant? The same standard solution each time, the same quantity of phenolphthalein, the same dilution factor if we are diluting, okay, our lemon juice. We'll work that out eventually, all right? The same type of lemon, we've mentioned that already, so I can't like get a lemon from one tree and another tree because they're going to be different, okay? All right. Constant. We also talk about not just what the variables are, but I also like to see how. How am I measuring that variable? How do I know it's not changing? What am I measuring it with? All right. So, for example, the titer value is measured with a burette, a volumetric burette, and it's basically we're trying to achieve a concordant titer. Okay, so we've got the variables covered. What else do we need to consider? Well, we haven't even done it yet, but hopefully at some point we have to come up with a hypothesis. All right, and really in the hypothesis we should have both the independent and the dependent variables. All right, somewhere in our hypothesis. So what could the hypothesis be if we are dealing with, say, a Lisbon lemon as an example? Anyone? How about this? The acid content in I don't know, we put in a number, 6% weight by volume, or, I don't know, 0.02 moles litre to the minus 1. You've got to come up with a number. Now, to help you with that, because you've done a bit of research, hopefully up there, one of the things you might have found in your research is sort of what's the level of acidity in a Lisbon lemon, maybe. Okay, you may come across that in the internet. Don't know, haven't done the research myself, but that's something you might have to consider in order to get an answer there. Okay, so research, variables, hypothesis, procedure, safety. What have we missed? Okay, we now have to talk about errors in our experiment. We have to address both systematic and random errors in all experiments, okay? So what are some of the systematic ones going to be? Systematic based on equipment, etc. So systematic, a good systematic error is, for example, the sodium hydroxide, because the sodium hydroxide, the concentration, if you're using it, can go up or down because it's absorbing moisture. Okay, we're also talking about cross-contamination because that affects the solutions that we are using, so we've got to be really careful, right, that we're not going to dilute or etc. rinse things properly, but that could be considered as a mistake also. Just think about that one. What other systematic errors could we have? Systematic unit titration. You'll have other things that will come up. If you looked at the handout that I gave you, pre-school holidays, it talks about things like, chips on the burette. Well, if I had a chip volumetric burette, I wouldn't use it. It's always going to measure inaccurately, but it will be inaccurately either above or below a certain volume because they're graduated not to have a chip in them. The same thing with the volumetric pipette. If that's got a chip in the tip, that becomes a systematic error that carries all the way through your experiment and it's biased in one direction. So think about other systematic errors, that could occur in your practical. If you're doing percent weight by volume, hopefully you're thinking, oh, wait a minute, I'm using a balance to do that. A scale, top pan balance. It does have systematic error in it. So that might affect your mass as well. All right, randoms. What are the random errors? Errors of procedure. No, you've used the word accurate. Accurate, we talk about systematic. Okay? We have to use the word precision for random. And so things like error of parallax, we know what that means. Remember we spoke about measuring volumes at eye level, so if you've got it there, it's going to be over the volume. If you're measuring from there, it'll be under the volume, so you have to allow for parallax error in both volumetric pipette, volumetric burette. That's a simple random error. What else could be a random error in the experiment?
Just wrong quantities.
Wrong quantities? Not really. Endpoint. Think of endpoint colour. Remember when we tried that experiment last week? And you had dark pink, light pink, and all these shades in between. So detecting the colour of the endpoint is going to be too dark, too light. That's going to be a random error, which means your titrations will go up and they'll go down. How do we improve that error? What do we do? We repeat the experiment, don't we? So how do we improve random error? Repetition, averaging results. We're after a concordant titer. Within 0.1 of a millilitre is concordant, if we can get one. If we are using multilitre and volumes, only. All right, other random errors, things that affect your results. Here are some other ones that you need to think more deeply about. Is this lemon old or is it just come off the tree? Do we know that? No, we don't. So, in order for us to understand that, an old lemon, I don't know, an old lemon might be more sour. It might have more acid in it compared to a lemon that just comes off the tree. I don't know. That's going to be variable. And has the lemon come from the top of the tree or the bottom of the tree? Yeah? Can we understand that this is probably going to have variable acidity levels? So when we talk about how we overcome that, well, we're going to have maybe a half a dozen lemons, that we're going to mix together, but the average we're going to get will be the average because we know there's going to be some random error in there. Not all lemons, I would assume, have got the same acidity. They're going to have some variability. Everyone cool with that? Right? And I guess it's the same with these, isn't it? So these may have some variable acidity, even though it's got a product information thing here. These might vary in acidity as well, for all we know. This, how would that vary in acidity? Been opened at all? Oh, it's pretty flat, this. So it's got not much carbon dioxide in it. Alright, so if I was going to do a titration with this, I'd probably need to do it within an hour or two of opening it, because by the time I come back to it tomorrow, it's lost a lot of CO2, so the acidity is decreased. It's got more alkaline, because carbon dioxide's escaped. Rocco?
So if you were to do that experiment
Good question. So if I do this, am I going to leave it open for a week and get rid of all the CO2? Well, the question is, what's causing the acidity? So when you work out what is causing the acidity in soft drinks, okay, you'll probably find that it's carbonic acid. So this has been carbonated. It's had carbon dioxide pushed into it, therefore it's acidic. So in other words, if I let it sit for a week, I'm going to have probably water. Maybe with a slightly lemon taste if it's lemonade. I don't know. That'll be an interesting thing to look at. Does the acidity change, okay, from 1 day to 7 days of sitting? All right? But that's another level of complexity again that you can introduce if you want to. We've got a few weeks to do this. Okay. All right, so what have we got? We've got some things we've got to do a bit of homework on, a bit of research on whatever we want the acid content in, how we're going to do it, what safety we need to consider, what are our variables, what's our hypothesis, what are our possible errors, not in any detail though, which is just a plan, okay, to lead us through the experiment. What else do we need to consider in a design? Anything else? No? We've got diagram down there. Josh? Yeah. Okay, one other thing you might want to consider is, how am I going to record my results? Am I going to put them into a graph or a table? So, how am I going to actually record what I'm measuring, okay, as I go? Alright, so that's important because you'll have a table of titration values somewhere. You might want a graph, like maybe you can graph, it depends if you're doing percentage weight by volume, you could graph each one. You could do first sample percent weight by volume, second sample percent weight volume, like we did for the acid content in vinegar, we could do that as well. What else? Results, research, variables, hypothesis.
The discussions.
That's down, the discussion's fine, that's in your practical write-up. Okay? Whenever you're doing this, but in your write-up you'll also have it, but you'll need to write a conclusion. And the conclusion really is, have you satisfactorily identified, proven or disproven the hypothesis? That's in your conclusion. How would you, or what have you found out? What things worked well, what didn't work well within the experiment? How would you change it? How do you think those things have impacted your results? Because, hindsight is something that we don't always have a chance to work from. All right? So this is what you'll be doing, all right, yourself. It's not filled in. It's a guide, yeah? But if you look in the assessment and sector, you'll see there's an example of one there for you, done from a Year 12 student for another practical. But they're all the same. So the deconstruction is something like that. There's no set order for it, but these are the key ideas. Hypothesis, errors, conclusion, procedure, results, safety, research, etc. All right? So that's what we need in order for you to get a bit of a handle on how am I going to do the experiment. And you can't, the beauty of that is you can't look up the answer on the internet because there's not one. Okay? You might find a few titrations, acid content in lemon, maybe. All right? You might find one, well you will find a lot, acid content in vinegar, but you won't find any for acid content in 7-Up lemonade. You won't find any for acid content in, okay, what are they called? Sour things, whatever they're called. Yeah. Any questions? We'll leave it there.